Okay, section 5.1 is the normal distribution and the standard normal distribution. So before we get into the normal distribution, let's say we have this symmetric frequency histogram. So thinking back to the frequency histograms, so it's symmetric because it would be a mirror image of itself over that middle point. So what we could do with this is we could approximate this by putting this other curve over top of it, this continuous curve. This continuous curve would be the normal curve. So the normal curve is a continuous curve, and it can be used to help us approximate certain percentages, and we'll see in a second probabilities for discrete distributions. So let's get into the definition for this. So like I mentioned, a normal distribution is going to be a continuous probability distribution for a random variable x, and the graph of the normal distribution is going to be called the normal curve. So this is the same thing as the bell curve that we quickly did previously. So here are the main properties of the normal distribution. The mean, median, and mode are all equal. It's bell-shaped curve and it's symmetric about the mean. The total area under the curve is equal to 1. And the curve is going to approach the x-axis, the horizontal axis, but it never technically gets there. So we call it, it asymptotically approaches it. So this is what it looks like. I'll be using just this representation of it. So the area underneath here is going to equal 1. And we can see I have the horizontal axis labeled. So the mean is in the middle. The mean will always be directly in the middle at that highest point. And then I also have over here on the right, whatever the so sigma, hopefully remember, is the standard deviation. I added one standard deviation, that's one standard deviation to the right. And then I added 2 standard deviations, so that's 2 to the right. And then I added 3 standard deviations, that's 3 to the right. I also subtracted a standard deviation from the mean, subtracted 2 from the mean, and subtracted 3 from the mean. So the way that we can always tell where one standard deviation is away from the mean, there is this point on this graph right here and right here where it changes curvature. That's called an inflection point. So that inflection point for every normal curve is going to be one standard deviation away from the mean, meaning if we took it and went straight down, so that one and that one over here, that is one standard deviation away from the mean, and that will always happen with this normal distribution with the normal curve. Okay, so doing an example here, let's find the mean and standard deviation of this following distribution. So we have the horizontal axis labeled, and it's clearly a normal distribution because of the normal curve. And I also have it labeled as x for the random variable. That just means that's essentially the data values. So the mean is always directly down the middle. So this is going to be the mean at 10. So mu equals 10. And to check one standard deviation away from the mean, we have to go to this inflection point. So it's that change of curvature. And we go straight down. And that's going to be, that represents mu plus sigma. So this distance right here is sigma. So that's a distance of 2. So sigma, the standard deviation is 2. Okay, and let's do a couple other examples here. So even though I'm going to be having essentially copying and pasting the same looking normal curve for most of these questions, technically the shapes can change a little bit, and they change based on the mean and standard deviation. So the mean and standard deviation of a distribution is going to determine the actual shape of the normal curve. So let's say we have these two curves right here. And with these two questions, for the first one, we want to know which of the following curves has a greater mean. So I'm going to label these curves. I'm going to label this blue one as curve A, and I'll label the red one as curve B. So for curve A, the mean is going to be right down the middle. And for curve B, it's going to also be right down the middle. So the mean for curve A, so I'm going to label this mu with a subscript of A, just representing the mean for distribution A. That's going to be 80. For B, I'm going to call that mu with a subscript of B, and that mean is going to be 50. So the one with the greater mean is going to be distribution A. Okay, next question, we want to know which of the following curves has a greater standard deviation. So we have to find each standard deviation approximately. It's not going to be perfect. So we go to that inflection point. I'm going to say for curve A, it's about right here. So then we go straight down, put us about right here. For curve B, it is about, I'm going to say about right here. Go straight down. So that's going to be one standard deviation away from the mean for that one. So for B, this distance is sigma. And for A, this distance is sigma. So I'm going to say sigma A is going to be approximately, it looks like it goes from 80 to 85. So 85 minus 80, that looks like a distance of 5. And then for sigma B, it looks like sigma B, the standard deviation for distribution B, goes from 50 to 60, so I'll say about 10. So we want to know which one was larger, and that's going to be distribution B. Let's say we have another example here. So certain distributions tend to follow this normal distribution, this bell curve, if we were to create a frequency histogram from the data. One of the distributions that tends to follow this pattern when given enough data is grades, so GPAs or test scores, assuming we have a large sample size. So for example, for this one, let's say we have test scores for an exam, and let's say we're told that they're normally distributed. The normal curve here represents the distribution of the scores. So we want to find the mean, and we want to estimate the standard deviation. So same questions as before. So for the mean, we go straight down, and that's the mean. For the standard deviation, we go to that inflection point. We go straight down, so that gives us that distance for sigma. So estimating this, we have a mean of 82%. So it's labeled as percents for the horizontal axis. And then it looks like sigma is 85 minus 82. Obviously, you can do most of these in your head, which would give us 3%. And remember that standard deviation has the same units as the data set. Okay, so now for the next thing here. This is the standard normal distribution. So it's the normal distribution standardized. So for every time we're using this standard normal distribution, it has a mean of 0. So mu equals 0, and a standard deviation of 1. So what this is going to look like is it's going to look just like a normal curve, because it is a normal curve, except the mean is 0. So you can see that we have labeled down here on the curve a mean of 0. And then we're adding a standard deviation to the right. We're adding another one and adding another one. So it goes 1, 2, 3. Adding 1, adding 1, adding 1. So the reason why we can keep on going, right? We can say 4 standard deviations to the right, 5 to the right. But if you remember the empirical rule, 99.7% of the data falls within 3 standard deviations from the mean. So we stop right there. We can see that we have most of the area, which is going to be most of the data, within 3 standard deviations from the mean. So just like before, we have a total area of 1 underneath this curve. And you can also probably see that I have that horizontal axis labeled with a Z. So this comes from the z-scores. So you may remember that we did z-scores for a little bit. So this horizontal axis is going to be z-scores, and z-scores, so this is really important, z-scores tell us how many standard deviations of value x is away from the mean. So that's what the standard normal distribution works with. It works with z-scores. So we're working with how many standard deviations a value is away from the mean. So for a mean of 0 here, with 0 in the middle, that means a value is 0 standard deviations away from the mean. Okay, so we're going to be using this z-score formula. Not really going to be using it too much today, but we will be for the next sections. So finding the z-score, which means we're standardizing a data entry x. Z equals that x value minus the mean divided by the standard deviation. So that is the z-score formula. Okay, so for this next thing is also really, really important here. Put a little star next to it. We're going to be using a table anytime we're dealing with these z-scores. We're using the z-score table. So each z-score on the table corresponds to a cumulative area under the normal curve at that value, which means the area to the left of the z-score. So when we're calculating a z-score going forward, we're going to have to round to the nearest hundredth because that's what the table tells us. So let's do some examples, and I'll bring up the table in 1 second. So using the table, find the cumulative area that corresponds to a z-score of the following. So we want to find the cumulative area for a z-score of 1.15. So once again, this means whatever the data set represents. We have a data entry that is 1.15 standard deviations above the mean because it's positive. So these are all going to be the standard normal curves. So 1.15 is going to be about right here, right? A little bit over 1. So what we're doing is we're trying to find the area to the left because that's what cumulative means. So we're trying to find this area to the left of that value. So we have to keep in mind that it's good to have an estimate before we do it. Keep in mind that the area underneath the curve is equal to 1. So if you had a guess, maybe you would guess this is about 0.8 or 0.9. So let's take a look at this table now. So here is the z-table that we'll be using. Obviously, this will be provided for everybody for all these questions. So we have z-scores. We have this table on the left and the table on the right. The table on the left tells us the area to the left of negative z-scores, and the table on the right tells us the area to the left of positive z-scores. Okay, so that's labeled right up here. So they tell us the same exact thing. It always tells us the area to the left, which you can see from these tables, from these little curves that they put in here. It's the area to the left. Okay. Let's zoom in a little bit. So for this one over here, so here are the z-scores. We have the column right here, and then we also have the 100th place value up there. So these are the z-scores. So all of those are negative z-scores. Let's take a look at the one on the right. These are the positive z-scores. So we can see these are all positive values. So the values inside the table are going to represent the areas underneath the standard normal curve to the left of the z-score. So if you look at these values inside of here, they're all between 0 and 1, which they always will be, because the area is either going to be 0 or it's going to be anything between 0 and a maximum value of 1. And you can also see the table on the left, all of those areas are between 0 and 0.5. Table on the right, the areas are between 0.5 and 1. Okay, so let's jump back to the question, because I don't remember what it was. So we're looking for the cumulative area underneath the curve for a z-score of 1.15. So we're looking for 1.15. It's positive, so we're using the table on the right. So we have to go over here. So here's 1.1. And then we have to go to the hundredths place value of 0.5, which is up here. So we have to see where they meet, which is right down here. So that is an area of 0.8749. So that's going to give us an area of 0.8749, which makes sense because the total area under the curve is 1. So that looks like it should be about 0.8 to 0.9. Okay, next one, let's look for the area underneath the curve to the left of z equals negative 0.24. So negative 0.24 is going to be over here. So negative 0.2 is right here, down here at the bottom. Oops. So it has negative 0.2. Hundredths place value of 4 is right there. So we see where they meet. And that tells us the area underneath the curve, which is 0.4052. So that area is 0.4052. And let's shade this in just so we know what we're talking about. So negative 0.24 would probably be about right here. So we're looking for the area to the left of that, so it looks like it would be this shaded in region right there. So our answer makes sense. It's a little bit less than 0.5. Okay, for a z-score of 0, the area to the left of 0. So before we even do this, we should have an idea of what the answer is. Keeping in mind that this distribution, this curve is symmetric, this is going to give us an area of 0. Or sorry, an area of 0.5, 0.5. If we looked it up on the table, it's actually on both sides here. It's right here. We have negative 0, which gives us 0.5 right here. And then it's also on the right. We have the 0.00, which gives us an area of 0.5. Okay, and then for the last one here, z equals 3.49. So 3.49 is really far over here. It's all the way to the right. So that's going to be this whole thing shaded in. So we should expect that answer to be close to 1. So let's look at the table. So 3.49 is over here on the right. So 3.4 is all the way down here at the bottom. 3.49 is all the way over here for the hundredths place value. So that's going to be all the way at the bottom right where they meet. It's going to be this value right down here, which is 0.9998. So this area is going to be 0.9998, which is what we expected because it was almost the whole thing shaded in. It looks like the whole thing shaded in for us. So far, we've just found the area to the left of a z-score underneath the standard normal curve. There's also 2 other types of areas that we can find. So there are 3 total. We can find the area to the left, which is what we've been doing. We can find the area to the right, or we can find the area between 2 z-scores. So those are the 3 types of questions that we can answer from this table. So let's do all 3 here. So to find the area to the left of a z-score, we use the table, find the cumulative area that corresponds to z, which is what we just did. So for example, if we wanted to do the area left of z equals 1.23, that would be 1.23 is about right here. So that would be this area right here that gets shaded in. That's the area we're looking for. If we look that up on the table, we would see that we would get a value of 0.8907. So that's what we've already been doing. So those ones are the easy one because the table tells us the area to the left. The other one is finding the area to the right. So to find the area to the right of a z-score, what we have to do is use the fact that the area to the right equals 1 minus the area to the left. So this is because if this comes from the fact that the total area underneath the curve equals 1. So the area to the left of a value plus the area to the right has to add up to 1. So the area to the right is 1 minus the area to the left. So for example, let's find the area to the right of z equals 1.23. So 1.23, once again, same value from last time is right here. So now we're finding the area to the right of it. So this is going to equal 1 minus the area to the left, which is going to be 1 minus the value on the table. The value on the table, we actually just found that, was 0.8907. So we have to subtract that from 1, which will give us a value of 0.1093. So anytime we're looking for the area to the right, it's 1 minus the area to the left, which is 1 minus the value on the table. Okay, last one is the area between two scores. So what we have to do is we have to find the area to the left of both scores separately using the table, and then subtract the smaller area from the larger area. So for example, let's find the area between z equals negative 0.75 and z equals 1.23. So we have to find their areas to the left, the area to the left for each of them, and then we have to subtract them. Larger one minus the smaller one. So the reason why we do this, so 1.23 is right here. When we look this up on the table, it tells us this whole area, right? But we're looking for the area between that value as well as negative 0.75, which is right here. So we need to subtract off the area to the left of negative 0.75, which will leave us with the area between them. So we're looking for that area between. So the area to the left of z equals 1.23 minus the area left of z equals negative 0.75, put parentheses around them. So the area left of 1.23, we already found this one right above, it's 0.8907. The area to the left of negative 0.75, look that up on the table, we would get 0.2266. So we subtract them and we get 0.6641. So if you subtract these and you get a negative number, chances are you just messed up and you flipped the order by accident for subtracting, so keep that in mind. Okay, so these are the three main types of questions. So let's do a page of examples here. So we want to find the area under the standard normal curve to the left of z equals negative 0.99. So let's fill it in on the table. So negative 0.99 is right here, pretty close to negative 1. So we're looking for the area left, so we're looking for that area. So this is going to be the area directly on the table because that's what the table tells us. So if we look this up in the table, I'll leave this to you guys so I don't have to switch back and forth. The area on the table tells us 0.1611. Okay, so for the next one, we want the area to the right of z equals 1.06. So 1.06 is about right here. We're looking for the area to the right. So area to the right means 1 minus the area to the left. So the area is going to equal 1 minus the area to the left, 1 minus the value from the table. The value from the table for that z-score is 0.8554. So we subtract them and we get an area of 0.1446. Okay, and then for the last one here, for this page, find the area under the standard normal curve between z equals negative 1.5 and z equals 1.25. So we're looking for the area, here's negative 1.5 between this and 1.25 about right here. So we're looking for the area between them. So we have to find the area to the left of both of them separately and then subtract it. So the area is going to be, the area between them is the area left of 1.25. So look at the table, we should get 0.8944. Minus the area to the left of negative 1.5, which would give us 0.0668. We subtract those, that gives us an area of 0.8276. Okay, so to do a couple more examples. So for the area to the right of z equals negative 1.35, negative 1.35 is about right here. We're looking for the area to the right. So we know it's going to be 1 minus the area to the left. So it's going to be 1 minus, and then the area to the left of that z-score, looking that up on the table, would give us 0.9115. We subtract them, it gives, oops, sorry, that's wrong. That's our answer. The area to the left is 0.0885. 1 minus that is 0.9115. Okay, and the next one here, we want the area to the left of z equals 2.25. So 2.25 is all the way up here. So we should expect this number to be pretty big because this is going to be most of the area shaded in. So since it's the area to the left, that's going to be the value directly on the table. And that's going to give us an area of 0.9878. Okay, last one here, we want the area between z equals 0 and z equals 1.85. So z equals 0 directly in the middle. 1.85 is up here. So we're looking for this area between them. So it's going to be the area to the left of 1.85 minus the area to the left of 0. The area to the left of z equals 1.85 from the table is 0.9678. The area to the left of z equals 0, hopefully we know this one now, it's 0.5. If not, you look it up on the table. Subtract these, we get 0.4678 as our area. Okay, so that is it for section 5.1, so make sure that you know how to read that z-score table, because we'll be using it going forward.